A modern smartphone screen functions as an active, high-frequency electrostatic imaging system. It projects an invisible grid of electrical field lines slightly above the glass. Because the human body is largely water and highly conductive, bringing your finger close to that grid intercepts those field lines. It bends and diverts a tiny amount of the electrical current through your body and down to the ground. For this interaction to feel instantaneous and natural, the entire life cycle of a touch event, from physical contact to the pixels reacting, happens in under 3 milliseconds. Within that 3 millisecond window, the device's hardware has to detect a microscopic electrical change. It measures a drop in capacitance of less than 1 picofarad. A picofarad is a unit of capacitance equal to 1/1,000,000th of a farad. This analog electrical disturbance is incredibly noisy. The system has to filter out the interference and convert that tiny voltage drop into a mathematically precise digital X and Y coordinate. Finally, that exact digital coordinate is packaged into a specific data format and sent over an I2C bus. I2C, or Inter-Integrated Circuit, is a hardware communication protocol that allows the touch sensor to transmit data directly to the host operating system. Understanding how this active electromagnetic matrix operates is the prerequisite for designing the next generation of bidirectional tactile interfaces. The physics of this system rely on the core capacitance equation, C equals epsilon times A divided by D. In this formula, capacitance equals the permittivity of the dielectric material multiplied by the area of the electrodes divided by the distance between them. When you touch the screen, your finger acts as a secondary conductive plate, creating a new capacitor and altering that overall value. Early touchscreens used an architecture called self-capacitance. In this setup, every individual row and column electrode measures its own capacitance relative to earth ground. This diagram illustrates a 2D grid matrix operating on self-capacitance. If two fingers touch the screen at the same time, the system registers 2 X coordinates and 2 Y coordinates independently. This creates 4 possible intersections, leading to a ghosting error where the controller cannot determine which 2 points are the actual physical touches. To achieve true multi-touch, modern screens use mutual capacitance. Here, the controller drives an electrical signal down transmit, or TX lines, and measures the charge that couples into perpendicular receive, or RX lines. A finger placed at a specific node diverts a portion of the electric field between those 2 lines to ground. This causes a quantifiable drop of less than 1 picofarad uniquely at that exact intersection. Self-capacitance generates a relatively strong signal, usually between 1 and 10 picofarads. Mutual capacitance yields a much weaker signal, but because every intersection is an independent sensing node, it allows the system to track multiple points simultaneously without any ghosting. By measuring the coupled charge at every unique intersection of the transmit and receive lines, the controller generates a high-resolution, 2-dimensional capacitive image of the entire screen. To physically build this transparent grid, manufacturers traditionally rely on indium tin oxide, or ITO. ITO is a specialized material that serves as the industry standard for transparent conductors. It offers an ideal combination of high electrical conductivity and optical transparency. However, its ceramic structure makes it inherently brittle. If you bend it, it cracks, making it unsuited for foldable devices. To solve this brittleness and lower the electrical resistance for larger screens, manufacturers are shifting to alternative materials like silver nanowires, known as AGNW, and microscopically thin metal mesh grids. These materials can withstand hundreds of thousands of bending cycles. This exploded 3D CAD model shows a traditional outcell display stack. Notice how it is built by bonding separate, distinct layers together: the cover glass on top, the optically clear adhesive, the ITO sensor panel, and finally the OLED display at the bottom. To assemble this stack, factories use optically clear adhesive, or OCA, which is a solid film, and liquid optically clear resin, or LOCA. These adhesives fill the microscopic air gaps between the glass and the sensor, preventing internal light reflections that would ruin the display's cost. This outcell method works, but it incurs severe optical and mechanical penalties. Every additional layer adds thickness, increases the overall weight, and multiplies the manufacturing complexity. To eliminate those penalties, display engineers developed in-cell and Samsung's Y-Octa architectures.
In these designs, the separate sensor substrates and adhesive layers disappear entirely. The touch sensor grid is patterned directly onto the OLED's thin film encapsulation, the microscopic layer that protects the organic light-emitting diodes from moisture. Collapsing the stack eliminates separate substrates and adhesive layers, reducing the display thickness and improving optical clarity. However, placing the touch grid millimeters away from the display's power-hungry, color-shifting pixels introduces massive electrical interference. The hardware can no longer isolate the signal on its own, shifting the entire burden of touch detection onto the digital firmware. That firmware runs on the touch controller IC, or integrated circuit. This chip is the algorithmic brain of the system, responsible for scanning the entire grid matrix at rates exceeding 300 times per second. This 3D topographic heat map represents the raw data frame output by the IC. You can see the chaotic electrical environment, a sharp peak where a finger is resting, a massive jagged plateau caused by a palm leaning on the glass, and random erratic spikes generated by ambient moisture or electromagnetic interference. To clean this data, the firmware runs a palm rejection algorithm. It analyzes the geometric signature of every shape, isolating and ignoring the large, irregular island of the palm while prioritizing the precise, circular peak created by the finger. The controller also relies on active signal conditioning. If it detects severe electromagnetic interference, or EMI, from a cheap wall charger or a cellular antenna, the chip uses frequency hopping. It dynamically switches its transmission to a cleaner part of the radio spectrum to dodge the noise. It even uses advanced logic to handle water, which is highly conductive. By analyzing both self-capacitance and mutual capacitance, the firmware can differentiate the static electrical profile of a water droplet from the active touch of a human finger. Even with clean data, there is a physical precision problem. The copper or ITO electrodes are spaced several millimeters apart. That grid pitch is far too wide to support pixel-perfect drawing or smooth stylus tracking. This diagram illustrates the solution, the weighted centroid calculation. By comparing the proportional capacitance drops across a 3x3 grid of activated nodes, the math calculates a precise subpixel coordinate that exists in the empty space between the physical electrodes. Once the exact X and Y coordinates are determined, the IC packages them into a Human Interface Device, or HID, report. HID is an industry-standard protocol used by operating systems to interpret inputs from mice, keyboards, and touch panels. This HID report is transmitted over the I2C bus to the host operating system, such as Android or Linux, which then triggers the user interface to respond. Physical hardware alone cannot provide seamless touch. It requires highly sophisticated digital filtering to extract a mathematically pure coordinate from a chaotic, noisy analog environment. The modern touchscreen is the product of mixed signal engineering, advanced material science, and high-speed digital filtering. Yet, despite this underlying complexity, the resulting user experience remains completely flat. You are still just tapping a featureless piece of glass. The next step in this evolution turns the touchscreen into a bidirectional, multi-sensory interface. Under-display biometrics show this shift in action. Ultrasonic sensors located beneath the screen emit sound waves that travel up through the glass and reflect off the microscopic ridges of your finger. This generates a high-resolution 3D map directly through the display stack. The ultimate bidirectional technology is surface haptics, developed by companies like Tanvis. This technology aims to restore the sense of physical touch to the digital world. Rather than relying on mechanical vibration, surface haptics utilize electrostatics to actively modulate friction directly under your sliding fingertip. This process is known as electroadhesion. As a result, you can physically feel the raised edges of a digital keyboard, the snap of a toggle switch, or the grit of virtual sand, all while swiping your finger across a completely smooth physical glass surface. By mastering the electrophysics of touch, engineers are closing the tactile loop. They are evolving the screen into a bidirectional, multisensory skin that merges digital information with physical sensation.